When sizing feeder conductors, it's essential to understand the interaction between conductor ampacity, equipment terminal ratings, and the requirements outlined in the National Electrical Code, specifically 110.14c. This section addresses temperature limitations at termination points. It stipulates that for circuits rated over 100 amps, or for conductors larger than 1 American wire gauge, the conductor ampacity must be selected based on the temperature rating of the termination points. This is a critical safety measure to prevent overheating and potential failures. Let's consider the specific example of sizing a feeder conductor and its overcurrent protection device. Imagine a scenario where the calculated load is 136 amps. The question arises, how do we determine the appropriate conductor size and breaker rating considering the 75°C terminal rating of an inverse time breaker? The key is understanding the application of 110.14c. Even though the conductor insulation may have a higher temperature rating such as 90°C with THHN wire, the circuit is rated over 100 amps. This triggers the requirements of 110.14c, meaning we must select the conductor size based on the 75°C ampacity. Looking at National Electrical Code Table 310.16, we can determine the ampacity of different conductor sizes at various temperature ratings. For copper conductors with THHN insulation, a 1/0 American wire gauge conductor has an ampacity of 140 amps at 75°C. Because this ampacity is greater than the calculated load of 136 amps, a 1/0 American wire gauge THHN conductor is suitable for this application. In summary, the conductor size was determined by the provisions of 110.14c, not solely by the inverse time breaker's terminal rating and not by the conductor's 90°C rating. The circuit's rating exceeding 100 amps necessitates using the 75°C ampacity for conductor selection. To further illustrate this principle, let's break down the calculation of the 136 amp load and explore alternative conductor sizes. The load calculation consists of several components: 46.2 amps multiplied by 1.25 plus 30.8 amps plus 30.8 amps plus 16 amps, totaling 136 amps. The 46.2 amp load is increased by 1.25 or 125% to account for continuous operation as required by the National Electrical Code for certain types of loads. The other loads 30.8 amps, 30.8 amps, and 16 amps are added to this value to determine the total load on the feeder. Given the calculated load of 136 amps and the requirement to use the 75°C ampacity rating due to 110.14c, we identified that a 1/0 American wire gauge THHN copper conductor with an ampacity of 140 amps is acceptable. However, let's consider what would happen if we used a smaller conductor size. A number 1 American wire gauge THHN copper conductor has an ampacity of 130 amps at 75°C. This is less than the calculated load of 136 amps. Therefore, a number 1 American wire gauge conductor would not be suitable for this application. It's crucial to select a conductor size with an ampacity equal to or greater than the calculated load, while also adhering to the temperature limitations specified in 110.14c. Now let's discuss the selection of the overcurrent protection device, in this case an inverse time breaker. The National Electrical Code generally requires that the overcurrent protection device be sized to protect the conductor from overcurrent. However, it's important to note that the breaker's terminal rating also plays a role in the overall system protection. In this scenario, the inverse time breaker has a 75°C terminal rating. This means that the conductors connected to the breaker must be suitable for operation at that temperature. We already established that the 1/0 American wire gauge THHN conductor is suitable for this application, based on its 75°C ampacity of 140 amps. The next step is to select the appropriate breaker size. The National Electrical Code typically allows for rounding up to the next standard breaker size if the calculated load does not correspond to a standard breaker size. However, it's crucial to ensure that the breaker size does not exceed the conductor ampacity. In this case, the calculated load is 136 amps. The next standard breaker size is typically 140 amps. Since the 1/0 American wire gauge conductor has an ampacity of 140 amps, a 140 amp breaker would be acceptable. However, it's also important to consider any other applicable code requirements or engineering considerations that may affect the breaker selection. For example, some applications may require the use of a smaller breaker size to provide additional protection. In summary, the selection of the overcurrent protection device must be based on the conductor ampacity, the equipment terminal rating, and any other applicable code requirements. It's crucial to ensure that the breaker size is appropriate for the load and provides adequate protection for the conductor. Now, let's delve deeper into the implications of 110.14c and its impact on different types of electrical systems. The requirements of 110.14c apply to various types of circuits, including feeders, branch circuits, and service conductors. The specific application of these requirements depends on the circuit's rating and the size of the conductors. For example, in a residential setting, branch circuits are typically rated at 15 amps or 20 amps, and the conductors are typically number 14 American wire gauge or number 12 American wire gauge. In these cases, the requirements of 110.14c may not apply, as the circuits are not rated over 100 amps and the conductors are not larger than 1 American wire gauge. However, in commercial or industrial settings, circuits are often rated at higher amperages and the conductors are often larger. In these cases, the requirements of 110.14c become more critical. For example, a feeder supplying power to a large piece of equipment may be rated at several hundred amps, and the conductors may be several 100,000 circular mils in size. In this scenario, it's crucial to carefully consider the temperature limitations at the termination points and select conductors with an appropriate ampacity rating. Another important consideration is the type of equipment being served by the circuit. Some equipment may have specific temperature limitations that must be taken into account when sizing the conductors. For example, some electronic equipment may be sensitive to heat, and it may be necessary to use conductors with a higher temperature rating to prevent overheating. Similarly, some types of lighting fixtures may generate a significant amount of heat, and it may be necessary to use conductors with a higher temperature rating to ensure safe operation. In addition to the equipment terminal rating, it's also important to consider the ambient temperature in the area where the conductors are installed. The ambient temperature can affect the conductor's ampacity, and it may be necessary to adjust the ampacity rating based on the ambient temperature. The National Electrical Code provides ampacity correction factors for different ambient temperatures. These correction factors must be applied to the conductor's ampacity rating to ensure that the conductor is suitable for the actual operating conditions. Furthermore, the number of conductors bundled together or installed in close proximity to each other can also affect the conductor's ampacity. When conductors are bundled together, they tend to generate more heat, which can reduce their ampacity. The National Electrical Code provides ampacity adjustment factors for different numbers of conductors in a raceway or cable. These adjustment factors must be applied to the conductor's ampacity rating to account for the effects of bundling. In summary, the application of 110.14c requires careful consideration of several factors, including the circuit's rating, the size of the conductors, the equipment terminal rating, the ambient temperature, and the number of conductors bundled together. It's crucial to consult the National Electrical Code and other applicable standards to ensure that the conductors are sized appropriately for the specific application. Now, let's consider some practical examples of how to apply 110.14c in different scenarios. Suppose we are sizing a feeder for a motor control center in an industrial plant. The motor control center has a total load of 200 amps, and the feeder will be installed in a raceway with 3 other current-carrying conductors. The conductors will be THHN copper, and the equipment terminals are rated at 75 degrees Celsius. First, we must determine the appropriate conductor size based on the 75 degrees Celsius ampacity rating, as required by 110.14c. According to National Electrical Code Table 310.16, a 3/0 American wire gauge THHN copper conductor has an ampacity of 200 amps at 75 degrees Celsius. However, we must also apply the ampacity adjustment factor for having 4 current-carrying conductors in a raceway. According to National Electrical Code Table 310.15, the ampacity adjustment factor for 4 to 6 current-carrying conductors is 80%. Therefore, the adjusted ampacity of the 3/0 American wire gauge conductor is 200 amps multiplied by 0.8, which equals 160 amps. Since the adjusted ampacity of the 3/0 American wire gauge conductor is less than a load of 200 amps, we must select a larger conductor size. A 4/0 American wire gauge THHN copper conductor has an ampacity of 230 amps at 75 degrees Celsius. Applying the ampacity adjustment factor of 80%, the adjusted ampacity is 230 amps multiplied by 0.8, which equals 184 amps. This is still less than the load of 200 amps. Therefore, we must select an even larger conductor size. A 250 kcmil THHN copper conductor has an ampacity of 255 amps at 75 degrees Celsius. Applying the ampacity adjustment factor of 80%, the adjusted ampacity is 255 amps multiplied by 0.8, which equals 204 amps. This is greater than the load of 200 amps. Therefore, a 250 kcmil THHN copper conductor would be suitable for this application. Next, we must select the appropriate overcurrent protection device. Since the conductor has an ampacity of 204 amps after adjustment, we can select a 200 amp breaker. This is the next standard breaker size below the conductor's adjusted ampacity. In another example, let's consider sizing a branch circuit for a receptacle outlet in a commercial building. The receptacle outlet is rated at 20 amps, and the branch circuit will be installed in a cable with 2 other current-carrying conductors. The conductors will be THHN copper, and the equipment terminals are rated at 75 degrees Celsius. Since the branch circuit is rated at 20 amps and the conductors are not larger than 1 American wire gauge, the requirements of 110.14c do not apply. Therefore, we can select the conductor size based on the 90 degrees Celsius ampacity rating of the THHN insulation. According to National Electrical Code Table 310.16, a number 12 American wire gauge THHN copper conductor has an ampacity of 30 amps at 90 degrees Celsius. However, we must also apply the ampacity adjustment factor for having 3 current-carrying conductors in a cable. According to National Electrical Code Table 310.15, the ampacity adjustment factor for 3 current-carrying conductors is 70%. Therefore, the adjusted ampacity of the number 12 American wire gauge conductor is 30 amps multiplied by 0.7, which equals 21 amps. Since the adjusted ampacity of the number 12 American wire gauge conductor is greater than the load of 20 amps, a number 12 American wire gauge THHN copper conductor would be suitable for this application. Next, we must select the appropriate overcurrent protection device. Since the receptacle outlet is rated at 20 amps, we must select a 20 amp breaker. In conclusion, understanding and applying the requirements of 110.14c is essential for ensuring the safety and reliability of electrical installation. By carefully considering the circuit's rating, the size of the conductors, the equipment terminal rating, the ambient temperature, and the number of conductors bundled together, you can select the appropriate conductors and overcurrent protection devices to prevent overheating and potential failures. Always consult the latest edition of the National Electrical Code and other applicable standards for the most up-to-date requirements and guidance. Remember to consult with a qualified electrical professional for any specific electrical design or installation questions. The National Electrical Code is a complex document, and it's important to have a thorough understanding of its requirements before undertaking any electrical work. By following the principles outlined in this discussion and consulting with qualified professionals, you can ensure that your electrical installations are safe, reliable, and compliant with all applicable codes and standards. Let's re-emphasize the importance of using the correct temperature rating for conductors. Firstly, using the incorrect temperature rating can lead to overheating and potential fire hazards. Secondly, it can cause damage to equipment and reduce its lifespan. Thirdly, it can violate electrical codes and regulations, resulting in fines and penalties. Always refer to the National Electrical Code Table 310.16 and other applicable standards for the correct ampacity ratings and temperature limitations for conductors. Pay close attention to the terminal temperature ratings of equipment and ensure that the conductors are suitable for those ratings. Remember, safety is paramount when working with electricity. By following the proper procedures and adhering to the applicable codes and standards, you can minimize the risk of electrical hazards and ensure the safe and reliable operation of electrical systems. Now let's briefly touch upon the impact of voltage drop on conductor sizing. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to increase the conductor size beyond what is required for ampacity. There are various voltage drop calculators and formulas available to help determine the appropriate conductor size to minimize voltage drop. These calculators take into account the conductor length, the load current, and the conductor's resistance. By carefully considering voltage drop during conductor sizing, you can ensure that equipment receives the proper voltage and operates efficiently. Furthermore, it is vital to consider the type of load being served when selecting conductors and overcurrent protection devices. Different types of loads have different characteristics and requirements. For example, motor loads typically have high inrush currents during startup, which can require the use of time delay fuses or circuit breakers. Similarly, lighting loads may have harmonic currents that can require the use of oversized neutral conductors. By understanding the specific characteristics of the load being served, you can select the appropriate conductors and overcurrent protection devices to ensure safe and reliable operation. Always consult with a qualified electrical professional to determine the specific requirements for different types of loads. Remember that electrical codes and standards are constantly evolving. It's important to stay up to date with the latest changes and revisions to ensure that your electrical installations are compliant with the current requirements. The National Electrical Code is typically updated every 3 years, and it's essential to have access to the latest edition. There are various resources available to help you stay informed about changes to electrical codes and standards, including industry publications, online forums, and training courses. By staying informed and continuously learning, you can ensure that your electrical knowledge and skills remain current and relevant. Finally, let's reiterate the importance of proper workmanship during electrical installations. Even if the conductors and overcurrent protection devices are sized correctly, poor workmanship can compromise the safety and reliability of the electrical system. Proper workmanship includes making secure connections, properly insulating conductors, and protecting conductors from physical damage. Always follow the manufacturer's instructions and use appropriate tools and techniques when performing electrical work. By paying attention to detail and practicing good workmanship, you can help ensure that your electrical installations are safe, reliable, and long-lasting. Electrical work should always be performed by qualified and licensed professionals.